first lecture of the afternoon session is the second lecture of Professor Huang on convergence in conformal field theory.
Okay, thank you very much. So I will continue my lecture yesterday. Actually, I discussed the convergence of products of intertwining operators. So the main tool is to show that these formal series actually satisfy differential equations of regular singular points. So then you see basically the convergence problems are really something like in mathematics we always have this existence problem. So for example, for a differential equation we have to have proved the existence. Everything will be based on existence. So here the convergence problem exactly play the same type of role. That is, we have to first establish convergence, then we can study the other property. So after the convergence is established, then we can actually prove the operator product expansion or the associativity of intertwining operator and so on. Okay, so I now want to start to share my iPad file so I can write. Okay, so this is actually from last time, yesterday's lecture. So we proved already the convergence. Now, just before, so today the main thing I want to discuss is the convergence of Q traces or pseudo Q traces of products of intertwining operators. But before I do that, let me just quickly mention that after this convergence is proved, we can, now you still have to do a lot of work, but I will not really get into this. We can prove the associativity of intertwining operators. So the associative intertwining operators is actually equivalent to the operator product expansions for intertwining operators. And this is also, see, because our intertwining operators, you see, when I discussed yesterday, also include in general logarithm. So this is also the logarithmic operator product expansion. So the associativity, basically, you can write this in this way. Y1, you have two intertwining operators corresponding to like conformal fields. And then you multiply them. So now because we proved the convergence, so this is well defined. Certainly the convergence is means that apply to some elements and then take pairing with element in the dual, but see we can just write as this product to be convergent, meaning that it is in that sense. The main thing that I want to emphasize that after you prove the products are convergent, we can also prove the iterate. So if you have two intertwining operator y3, y4, w1, z1 minus z2, w2, z2. Okay, we can also prove that this iterate is also absolute convergent, but the convergence region is z2 bigger than z1 minus z2. Okay, so this can be derived from the convergence of the product. And then the associativity of an intertwining operator basically says the following. It says that given two such intertwining operator, you can find, okay, given two intertwining y1, y2, you can find two other intertwining operator y3, y4, such that this is equal to this in the intersection of the region, z1 bigger than z2 bigger than, because the left-hand side is convergent only in this region, right-hand side is convergent in the other region. So this way, in the intersection, both are convergent. to some analytic functions. These two analytic functions are equal. So that's the meaning. Okay, you can also formulate in the other way is that you can say that because these can be analytically extended to a multi-valued function. And this can also be analytically extended to a multi-valued function. So the associativity says that these analytic, the multi-valued analytic functions are equal. So you do not have to specify region because now they are actually analytic function on the whole region except the singularities. Okay, so the singularities are actually the same for iterate and for the product. So we have two analytical functions are equal. Okay, so either way is fine. So now, this is basically using this. Okay, in the construction of the tensor category on the module on suitable module categories for vertex algebra. If we only talk about the braided tensor category, the most difficult part is to construct the associativity isomorphism. Okay, so then essentially, okay, the associativity isomorphism is equivalent to the associativity of intertwined operator. Okay, so this is something that I want to mention. Okay, so the next topic I want to discuss is this convergence. Of the in general it should be pseudo traces, but in the case of a rational conformal field theory, we only need to take the Q traces. So I put parentheses here. Okay, so this is what I want to discuss today. So if I have more time, I will also discuss the other convergence results. But this is the main thing, and this is actually more difficult than the product of an intertwined operator. So let's first look at the problem. Okay, what is the main problem for us? Okay, so the main problem is the following. The intertwined operators corresponds to so-called a three-point function. So three-point function basically can be described using something like the sphere with three punctures. This is 0, this is z, and infinity. So actually, we do have to consider some local coordinate, but see in genus 0 and genus 1 case, the simplest case for us to study is to consider the trivial local coordinates. Okay, so because these are just a complex plane, just a map to the same disk, it's the trivial. But see, just to make sure that the local coordinate vanishing at these punctures. So intertwined operator corresponding to this geometric object. So when we compose two intertwined operators, they're like a product of an intertwined operator. It actually corresponds to, so let me draw this here. If I take the product of two intertwined operators, what I will get is some function corresponding to this picture. This is infinity. With the trivial local coordinate, and this is C1, this is C2, and this is 0, trivial local coordinate. Okay, if you compose them, so it's a sort of like a you actually have can cut some circle here, and then you separate into 2 parts. One part corresponding to such a sphere, each part corresponding to such a sphere. So you can just solve them to get this one. And here you see the reason why for inter-20 operator product, the convergence must be held when the absolute value of Z1 shall be bigger than absolute value of Z2, because if you use this cut, Z1 must be above this circle, and Z2 must be below this circle. So there should be such a circle existed. So that's why the absolute value of Z1 must be bigger than absolute value of Z2. So this is a very very nice geometric picture here. So it is a very faithful sort of the reflection of the geometry. Okay. So now, so we see that for the products of inter-20 operator, and also iterate, you also have this geometry interpretation. Then you see the main thing that we want to go to genus 1, okay, because it's natural that Riemann surface, when you do solving, it will automatically give you genus 1 surface. Okay, so how do we get a genus 1 surface? Like in this surface, we actually cut a disk here. Using the local coordinate, we can cut a disk here. And then cut a disk at the infinity. And then we identify the boundary. Okay, so suitable way of identifying boundary, and then we will obtain a torus. So this is the way to get torus geometrically. So we want to know what happened in algebra. So the main thing that this way of describing a torus is not the canonical way we are actually using. So basically, after you cut this disk and this disk, you actually have an annulus. Okay, so we actually have some number here, which is Q. When you identify this circle with the circle outside, you actually identify Q with the number 1 here. This is number 1. This is a unit disk. Okay, so this disk, the radius is certainly equal to absolute value of Q, and this larger disk is 1. So the description of this surface after you cut is given by such annulus, and then you identify this Q with 1 and so on. So you'll get a torus. But this is not the usual way for us to describe a torus. The usual way to describe a torus, we always use this parallelogram. Okay, so here it's 1, here it's tau. This is on the complex plane, and this is 0, and this is certainly 1 plus tau. And then the main thing that now we identify this boundary with this boundary and this boundary with this boundary. So we get a torus. This is the canonical description of a torus. So the main thing that if we start with some inter-20 operator, we want to do something like go to the torus. We have to use it. We actually want to use the usual description in terms of tau. So there is actually a conformal transformation we need to use. There's a conformal transformation. Okay, this conformal transformation is actually, okay, this direction, there is actually certainly you actually have an inverse. This direction is I think it's like a logarithm. If the global variable is w, so it's something like the logarithm w over 2 pi I, and the other direction is e 2 pi I. Say maybe y. Okay, so because the variable is different. So we actually have this conformal transformation, which transform this to this. So this is something that we need to use. Okay, so now what we do, the main thing that we actually consider product of an inter-20 operator. Product of inter-20 operator exactly give us this picture. This is sphere picture, or this annulus picture. There with some points like Z1, Z2, but we have to actually have to have to map this to this parallelogram. And therefore, you see, when we write down these products of intertwining operator, like y1, so here for simplicity, let me write out only the product of 2. Okay, product of 2 is actually, 2 intertwining operator is actually quite typical because for n, product of n, the proof are all the same. For only 1 intertwining operator, actually, it becomes really simple. It's much simpler. So the product of 2 is actually a very typical case. So the one thing is that the variable here, we should use 2 pi iz. Okay, because something like here you have a puncture, and then you see if you want to use intertwining, you have to map to here to use the intertwining operator to describe, and therefore this variable originally the point here should be equal to e 2 pi iz because it's mapped from this parallelogram to this annulus. So this is the one thing. The other thing is the following. See, when we actually have intertwining operator, I said that we actually have this trivial local coordinate here. Okay, but see on the when we describe like on this parallelogram, if you originally use the trivial local coordinate, after the conformal map to here, it will not be trivial. Okay, so the difference is that originally, if you just use intertwining operator, the local coordinate around this z1, z2, they are trivial, but we wanted to use the parallelogram to describe this, and we want to use the trivial local coordinate here, and then if you map to the annulus, you will actually have some non-trivial local coordinate, and this non-trivial local coordinate is given by some operator. So this is, I will just write down the formula, but let me first write this ui z1. It depends on z1, and then apply to w1. Okay, here this u. Okay, u of in general, if it depends on some variables, and let me say x. This is equal to 2 pi I. This is coming from this conformal transformation, and e minus sigma j is in z plus the positive integer aj lj. Okay, so this is only have a positive action. So when it acts on some element, because our modules are always lower bounded, so when j is sufficiently large, or when you have exponential, you will expand this. When there are enough L take product applied to some element, it will become 0. So because these Lj lower the weight, right? So this is a well-defined operator from W to W, from a module to module. And what are these Aj? The Aj are given by this formula. It's like we write on this formal series. This is a formal series in Y, and this can always be such a formal power series. This is really a power series. Can always be written as E sigma j in Z plus Aj Y j plus 1 d dy. Okay, so this is something that you can expand this as a series, and then you can solve equations to obtain these Aj's. So these Aj's are uniquely determined by this formal series. Okay, so we have this operator. So the way we write our intertwining operator for our genus 0 correlation function, we have to use this. Okay, so now what we do is that we need to take a trace. Basically, the process of identifying this boundary, this circle with the outside circle, algebraically it corresponds to taking a trace. Okay, but trace over the module. See, we have 2 into 20 operator. So here I have to put e to pi I c1 w1 e to pi I z1, and then multiply another into 20 operator, because I do want to discuss the case of 2 into 20 operators. C2 applied to W2 and e to pi I C2. Okay, then you see the we have to take the Q trace, so it's QL0. Okay, so this is a natural thing. You just put QL0. Actually later we see that we have to modify this, but this is something come very naturally. Naturally, we do not have to put this by hand. Later in the formula we use, we see that we have to put minus c over 24. So everything is really conceptual. This minus c over 24 actually coming from, it's also coming from this conformal transformation. Okay, this conformal transformation. So that's the reason. Okay. So the first problem is that see the main thing that this trace should describe the corresponding correlation function on the torus you obtained by just identifying these 2 boundaries. So we will actually have this torus, but here is one should be careful is this. See, when you do this sewing, identify the boundary, actually you get a torus, but you also get a circle, because this is the circle that you used to identify these 2 boundaries. Okay, this is these 2 boundaries corresponding to this one circle. So the torus we get is actually a torus together with such a circle. Okay, and so here the problem is this: we want to construct the correlation function. Certainly there are also 2 points here. We want to construct correlation function associated to such the genus 1 surface with punctures and the local coordinates. Okay, now the candidate is just this. Okay. So there are 2 problems we need to solve. The first problem, it's the most basic problem is that we have to prove the convergence, because this time module is in general certainly infinite dimensional. When you take infinite dimensional trace, you have to prove convergence. We do not know anything. This kind of operator, our module is just a graded space. So we do not have any other structure. For Hilbert space or even some weaker space, we can indeed talk about a trace class operator. But first of all, we do not have Hilbert space structure, and even if we have some topological completion of the module structure, this can be done. We still do not know whether these products are of trace class. So we have see, in some sense that there's another approach to conformal field theory is the method of using conformal nets. So in that approach, certainly you work with the operator algebra. So it seems that you do not have to prove a lot of such convergence results, but actually you still need to do the same thing, because you have to first make sure that all the operators you work with satisfy all the nice property, and therefore these corresponds to this type of property. So here we have the first question is that whether this is convergence, okay, and if it is convergent, we wanted this to be convergent to a analytic function on the moduli space of such torus. Okay, so there is first of all if this is convergent, we have to make sure that this can be analytically extended. Okay, it's not just for those Z1, Z2, and Q in the region of convergence. You have to be able to analytically extend it. Second is that if you will want this to be defined on the modular space, then see this trace or the something formed by these traces should be independent of this circle. You see, the modular space of torus is independent of such circle. See, when you have such a circle, it is actually corresponds to so-called Teichmüller space. It's not modular space. So that is the next step. That's the prove the modular invariance. If the modular invariance is proved, this individual trace still depend on this circle, but see the vector space formed by all these traces is independent of the circle. Therefore, it's defined on the modular space. Okay, so I will not talk about the proof for the modular invariance part. Okay, that part is not what I plan. What I want to discuss is mainly the convergence. Okay, the convergence is actually the first thing you have to prove. Without convergence, you cannot do anything. So certainly people can still derive a lot of results. That is, you assume the convergence. We can derive really wonderful conjectures. All these conjectures actually see this is the convergence together with the modular invariance is indeed one of the most fundamental assumption or conjecture in Moore-Seiberg's paper. So you can see that in their paper, the operator product expansion and this modular invariance, and which includes the convergence, are explicitly stated in Moore-Seiberg's paper. So as an assumption, they didn't really say why this is true. So okay, so now see we want to prove this. Okay, now for before I discuss how this should be proved, I will first want to discuss the more general case, because the trace is good enough if we study so-called rational conformal field theory. Rational conformal field theory, in rational conformal field theory, all the modules for vertex sobre algebra we are interested is a direct sum of irreducible modules. So therefore, you can just take the trace to be over only those irreducible modules. Okay, and an irreducible module has this really wonderful property that is on irreducible modules, any operator commutes with the action of vertex operator must be proportional to the identity. You will not be able to find any other non-trivial operator acting on a module, an irreducible module, which is not proportional to the identity. So because of this, so we actually sort of like just to take the trace is good enough, because yeah. So here the main thing that the trace corresponds to is associated to so-called trivial algebra acting on the module and commutes with all these vertex operators. So this is because irreducible module we always have the Schur's lemma. But so this is for rational theory or semi-simple case. Now see for many years one of the main interests is in this non-semi-simple or non-rational theory, the logarithmic theory. Logarithmic theory, the main thing that in general the module in our category cannot be written as direct sum irreducibles. So you have these composition series. So in this case, okay, there can certainly be a lot of operators which acting on the module and commutes with all the vertex operator, which are still non-trivial operators. So if you have a lot of non-trivial operators, these themselves form some algebra. Then see we can actually take trace using these algebra. So this is the some notion in the theory of associative algebra. People already have this kind of pseudo trace. But see the Miyamoto is the first person who actually applied this to the study of these in the case of vertex algebra, and then the using pseudo Q traces. So let me briefly describe what is a pseudo trace. So the main thing that if we have a module for W, certainly it should be graded. In general, it's in C, but in our case, it's always like we only have a finite limited congruence class. So there are not too many non-integer numbers. So if we have a W, then we certainly have this vertex operator map, and then see we actually if this is not irreducible, then in general it is always possible that we can have some finite dimensional. So usually we need a finite dimensional associative algebra, which acts on the module also. Okay, so here is we also require that this finite dimensional algebra acting on the module to be actually commutes with the action of the vertex operator. Okay, this in general, if this is not semi-simple, then see it is certainly possible. So because this commutes with the action of vertex operator, we will write the action as the right action, because right and the left is sort of when you write, it's supposed to be commute with each other. So we always write P, the action of P from right. So W now is a V module, but also a right P module also. Okay, and then see we also require that for each of the homogeneous subspace. So here is actually we do require these modules, the homogeneous subspace, to be finite dimensional. Okay, so we want this P acts on these finite dimensional pieces. So the main thing that P should commute with these vertex operator including the Virasora and including L0. So certainly P commutes with L0. Therefore, P actually acts on this homogeneous subspace. And we assume that these Wn are projective as P modules. So this is something that if we want to define pseudo trace, we have to require this projectiveness. So now, if we have such a projective module, then see we have a so-called a projective dual basis. So on this module, we have basis Wi and also Wi prime, which is from the harm P2 from this Wn to P. Okay, so we actually have this is just like the dual basis, but see it's not the dual is not mapped to the C, but it's instead mapped to P, such that every element in this module can be written as usual if you have a dual basis like a Wi prime P. This is the W. Okay, so here this is the element in P, and because we consider this as a right module, so it acts from the right. Okay, so using the this dual basis. And also we need another ingredient. This is the symmetric linear function. So what is a symmetric linear function on P? So it is a map from P to C. It satisfies this symmetric property. It's a linear map, certainly. Phi PQ is equal to phi QP. Okay, so this is a symmetric linear function. And then using this symmetric linear function, we can define the pseudo trace. So the pseudo trace is just using a phi because it depends on the choice of such symmetric linear function over, say, for example, Wn. So because I use this finite dimensional space. If you have an operator, okay, any operator on this finite dimensional subspace, alpha, then this pseudo trace is defined to be phi sigma I equal to 1 to. So, okay, I do not need to write down how many of them, just to take a sum over I. And then Wi alpha Wi prime alpha Wi. So this is completely just like the usual trace, right? So you apply this alpha to the basis elements, and then you take the dual, the pairing with the dual basis elements. Okay, so this is a pseudo trace. So now we should, in general, we really should consider instead of the trace above, we should consider this kind of pseudo trace. So we have to choose some kind of a. We first have to choose a associative algebra, finite dimensional associative algebra P, which actually commutes with the action of our vertex operator on the module W. And we also have to choose a linear function, symmetric linear function on this finite dimensional associative algebra P. And then we can take the pseudo trace of this Y1, this U e to pi I. So this part is the same. Okay, now at this moment, temporarily, let's still put just the L0. Okay, so here, another thing I need to explain, because in the general case, the module are not semi-simple. So L0 also are not semi-simple. L0 has the diagonal parts, semi-simple parts, and the nilpotent parts. So the you have to like QL0 you have to separate into the diagonal parts, which acts just as usual by the eigenvalue, and nilpotent parts you have to use the exponential to expand this, but because it's nilpotent, when you expand using exponential, it has only finitely many terms. So that's that's well defined. Okay. So our goal is to discuss the convergence of this. Okay. So now one thing I want to mention that we already have the convergence of the product of an intertwining operator inside. Okay. So the main thing that we need to prove the convergence is this as a series in Q. This is as a when we first write on this trace, this is really a formal series in powers of Q and also logarithm of Q, because in general we have this nilpotent part, so we have logarithm of Q. Okay, so let me just before I discuss the proof, let me just give some historical discussion. So the first results on such convergence is by Zhu in his actually thesis later published. So Zhu actually, but he didn't prove this this general case. This convergence or modular invariance is first formulated by Moy-Seiberg in the paper. To prove the special case, that's the case that certainly in Zhu's case, he only proved the rational case. So we do not have to take the pseudo trace. So he proved that this case, the intertwining operator are nothing but, so I do have to write something here. So the main thing that he actually only put e to pi I c1 L0 here, v1. This is in the algebra, e to pi I 1 and a yw e to pi I c2 L0 v2 e to pi I. Okay, and then QL0. Okay, so he actually discussed only this special case. This is very special because the YW is the vertex operator acting on the module. So this case, it's special because especially make things special is because we know that these YW contain only the integer powers of the variable. Okay, this is not multi-value function. These are single value function. The product actually give us this rational function. So he proved this case, but he also have to first prove it. See, this is much more difficult than the genus zero case, because in genus zero case we see that the proof of convergence for the modules are very easy. Okay, this time it's already even in this case it's not easy. So the what Zhu did is the following. He actually did the following. He actually first of all he actually find some recurrent relation. So he actually used some recurrent relation to reduce this trace of two. So in general, certainly n vertex operator. He used a recurrent formula to reduce this to the proof of the convergence only one vertex operator. Okay, so how he achieved this is because these vertex operator, they satisfy in general, they satisfy so-called Jacobi identity. Okay, but in particular vertex operator, we all know that vertex operator have the commutator formula. Okay, this is really the commutator formula actually give, in a special case of our affine algebra, give the commutator for affine algebra. So we have commutator formula for vertex for modules for vertex operator. He actually used this commutator formula. He can obtain some recurrent relation. So you reduce to prove the convergence of this. And then for this convergence, he derives some differential equation. Okay. Now, then you see the actually Miyamoto actually just to try to generalize this. So what Miyamoto did is the following. He's something like he also in the rational case. So we do not need to consider the pseudo trace, only the trace. But roughly speaking, Miyamoto considered the case that one operator is the intertwining operator, but all the other operator is the vertex operator on modules. Okay, so then there's an intertwining operator here. So for see the in general, certainly Miyamoto, just like a Drew's case, it can be n vertex operator. Miyamoto can have n minus 1 vertex operator acting on module and 1 intertwining operator. So essentially, the proof of the convergence is the same as Drew's proof, because for one vertex operator and a 1 intertwining operator, between 1 vertex operator and a 1 intertwining operator, we still have a commutative formula. That's actually coming from the definition of intertwining operator. So we can use you can derive, basically use the same calculation, you can derive recurrent formula, and then you reduce to the trace of a 1 intertwining operator, and then you use the same differential equation, one can actually prove the convergence. Okay, so this is Miyamoto's generalization. And then Miyamoto, again, he generalized to another case, is that in the case that modules are not computer-reducible. So then he introduced the trace, the pseudo trace, okay? And then you still, so in this case, he only considered, just like a Drew's case, only consider the vertex operator for modules. This is the B1. So in this case, he didn't consider the intertwining operator, just the V1 e to pi I. Okay, so here the convergence part is still the same as what Drew did. Okay, because still for these module vertex operator, we still have commutative formula, and you can still reduce to 1 vertex operator and then prove a convergence. So the main difference is that now we can he actually introduced the pseudo trace. And then the pseudo traces satisfy the same property as trace. So every property you used for trace can still be used. So the convergence part is the same as Drew's proof. The main sort of complicated part is that we have to prove a modular invariance. Then you have to use some property of the pseudo trace. Okay. So now, actually, after these things, modular invariance, these convergence results are proved. Then you see I think that the people encounter some main difficulty, because if we wanted to really, okay, just like here, we wanted to, so even for just the trace, okay, if we want to prove the convergence, Drew's method, see the original Drew's method does not work. The reason is this: commutative formula for vertex operator only holds when the vertex operator have integral power of the variable and without logarithm. Here we have non-integral power of this variable, and then see there's no commutative formula. We cannot really find nice commutative formula. So because there's no commutative formula, you cannot reduce the proof of the convergence to the trace of 1 intertwining operator using this method. Okay, so Drew's recurrent formula method does not work. So in the beginning, this is something that this is an obstruction for actually prove this convergence. Okay, so this is then see this is problem. So after a number of years. So the main thing that the difficulty is not just to prove the trace is convergent. Also, in the beginning, we even do not have the convergence of the product of intertwining operators. So we actually need to first prove the product of intertwining operators is convergent, then prove this. So then see later, I do find a way, instead of using Drew's method to derive a recurrent relation to reduce this to trace of one vertex operator or one intertwined operator, I actually directly prove the product, then take the trace to be convergent. And later, Fiordalisi generalized this to the pseudo trace case. Okay, so this is the some historical discussion, but I think this is quite important because sort of like the main thing that if you have very nice intertwined operator, like the intertwined operator for the vertex operator for the module, when you have a nice vertex operator, you can use some use some simpler method. Okay, this method allow you to derive some recurrent relation and prove this. But unfortunately, for general intertwined operator, you cannot use this method. So in some sense, this is similar to like in the case of modules for vertex operator algebra, the proof the product of two vertex operators to be convergent, we can use this kind of locality as I discussed in the beginning of the lecture. But when you get into the general intertwined operator, that method does not work. So here it also does not work. We actually have to directly derive the differential equation. Okay, so now let me discuss the proof. Okay, so now I want to discuss the proof. So the main difficulty of the proof is mainly because we actually have to prove some formula. See, just like in the case of product of intertwined operator, I wrote down one formula. Okay, basically I say that there's this formula, then you can prove three other formula. These formulas can be used to reduce the this kind of a trace, this kind of a series, the formal series, to only finitely many of them. So because we have only finitely many of them, so we actually obtain a module over these finitely many series, and so it is a finitely generated module over a suitable ring. And then when you take the derivative, because we have a L-1 derivative property, it is still equal to such a series, and each such a series is a linear combination of these generators, and therefore the derivative is also linear combination of these generators. So this is one way to prove the differential equation. Another way is that given any such a series, you take the higher order derivatives, arbitrary order derivatives, and these derivatives form a sum module, and the sum module is also finite generated, and therefore they are linearly dependent. So you get differential equation. You get a higher order differential equation. Okay, so here the general idea is the same, but it's much more complicated. Okay, so first of all, let me write down one formula. So I feel that if I do not write down any formula, the formula is complicated. So it's long, but I feel that I still want to write on this, even though you don't have to sort of understand the details because I do not give a proof, but at least you will get some feeling. So the formula is this. Okay, so we actually wanted to discuss this kind of, in general, it's a pseudo trace. So for the convergence part, the proof is actually for the pseudo trace is almost the same. It's a little bit different because L0 is not the same simple, but it's almost the same. So what we want to consider is the pseudo trace of such intertwined operator. So here you see that you probably already noticed that in juice the proof of the trace, he actually do not use this U. He actually just use e2 pi I z L0. Here, see that because he uses only the e2 pi I z L0, so he actually have to change the vertex operator. He actually have to do a coordinate change of vertex operator, so you get isomorphic vertex operator, which is isomorphic to the original vertex operator, but the vertex operator map is different. So I actually here use this one to actually avoid to change to the isomorphic vertex operator. And also we do not see, because we are discussing inter-Turing operator. So for some important purpose like genus 1 associativity, I do not have to change the variable for the inter-Turing operator, which is much more complicated because it's a multi-value function. So this way avoid this type of complication. So here it's I do use this. Now the main thing is that we now want to consider, instead of, because okay, so let me just write down this formula first. Let me write down this first. W1. So this is V2. Just to remember, V2 is is one coefficient of the vertex operator acting on W1. Okay, so what we do is that we actually want to look at what happened when V2 applied to W1. Okay, remember in the case of a product inter-Turing operator, I actually used the V minus 1. So what is the reason? The reason is because of this. Basically, if you have, so just to recall, the residue X minus 1 YW V XW. This is what we denote as the U minus 1 W. Okay, and then the X minus 2 YW. U minus 2. So see that the here, this is a rational function with a pole at x equal to 0, whose order is 1. Okay, so on the sphere, the rational function, the order of the pole, the smallest order is equal to 1. So that's why we take x minus 1. But on the genus, so this is, we do want to actually study genus 1 correlation function. On genus 1's Riemann surface, if you have a meromorphic function, you cannot have a pole whose order is equal to 1, right? So the order is at least 2. So like the main example is certainly the Weierstrass P function, which has a order equal to 2. So that's the reason. Okay, so now we actually can explain the reason why. Okay, see when I want to prove the convergence, instead of the C1 cofinance, remember when we actually prove the convergence of product into Turing operator, it's the C1 cofinance we actually use. We assume all the modules are C1 cofinite. So here we have to use the C2 cofinite. So C2 cofinite just means that the given a module W over C2 W, this dimension is less than infinity. What does this mean? This means that almost every, except for finite dimensional subspace, almost every element in W are inside this C2W. And what is C2W? C2W is just the linear span of U minus 2W. Okay, so here we actually will only actually obtain nice formula when we put V minus 2. Okay, so this is the reason. And then see, I want to actually just the mention that the first cofiniteness condition in vertex algebra was actually first discovered by Zhu. So in his paper on the modular invariance. So he actually discovered this now we call this C2 cofiniteness. So he discovered, see, C2 cofiniteness is very useful. We can use this to study modules, and we can prove a lot of things using C2 cofiniteness. But I think that most people probably more familiar with C2 cofiniteness, the application of C2 cofiniteness in the study of modules and so on. But actually, the first of all, the C2 cofiniteness is exactly discovered when Zhu he wanted to prove the convergence in his modular invariance theorem. He actually realized that if you wanted to prove the convergence of trace of one vertex operator, because he used the recurrence relation to reduce everything to trace over one vertex operator. And if you want to prove the trace of one vertex operator is convergent, he has to add such a condition. Okay. Originally, he thinks that this condition one might be able to derive from some other assumptions, but actually, I think that this type of conjecture is still not proved and probably not true. So this become an important condition. And then see that we also have these C1 and even Cn cofiniteness. So the main thing that these cofiniteness, the function of these cofiniteness, the main use of these cofiniteness are really to the proof of convergence. So they can certainly be used to prove other very nice property, but in some sense that these other properties in many cases can be proved also using without using these condition or using some relatively weaker condition. Like for example, originally people actually constructed a twisted module. You actually have to assume the vertex operator satisfies C2 cofiniteness. But in recent years, I actually constructed a twisted module without any condition. So this kind of condition is very nice, allow you to prove stronger results. But the main use is really the convergence. Okay, so now this is something that should not be in the formula. So the formula I want is that this trace with W1 replaced by V minus 2 W1 is equal to the following. So first of all, it's minus sigma K in Z plus and 2K plus 1. Okay, here we have this is the notation of Zhu, so I use this notation. This is basically the modular function G2K plus 2 tau, but see here everything should be expanded as a series in Q. So this is really the Q expansion of the modular function, the Eisenstein series, right? So this is the Q expansion. Okay, so here the Q expansion is important, and then you would take the trace, pseudo trace of Y1. Okay, here it's still we have this operator, and here it's just a W1 because we actually basically want to move to the other W. Y2. Okay, here we have V2K W2 and then Q as 0. So this is the first term. Okay, now so just to observe one thing is that now this K is positive. When V2K acting on W, it always lower the weights of W2. So that's important. And then the second term is plus sigma m in n. This is a non-negative integer, and here it is minus 1 to the m, and now here we have minus m minus 1. Now this is and again I use Joule's notation, m plus 1 z2 minus z1 q. Okay, so what is this? So first of all, for the Weierstrass p function, we have derivatives. So this is sort of like the when m equal to 2, m equal to 1, this is just a p2. P2 is the Weierstrass p function, and then for higher m plus 1, they are just the derivatives of the Weierstrass p function. Okay, so like a P3, it's the first order derivative with some like minus sign and some coefficients, but that's not important. So what is the tilde? And also put Q here. These Weierstrass p function and their derivative, they also have Q expansion. So this is the notation Joule used to denote the Q expansion. So here we have these, and then we have this pseudo trace of the y1 of u. This part is the same. Because basically we want to move everything to the other, to act on the other elements. And then y2. Cu e to pi I c2. Okay, so here I have to change this. This now is vmw2 e to pi I c2. Okay, so then ql0. Okay, so now yeah, so this is the formula we actually need. Okay, so this formula is the formula similar to what I wrote down for the proof of the product of intertwinning operators. So let's look at this. The main thing is that originally we have this element, this V2 applied to this, and then see it will be equal to these. The main thing is that these always and a Vm, m is a non-negative integer. These always lower the weights. Okay, so therefore, originally we have a V2 W1 here. After you equal to the other one, these weights of the elements become smaller. Okay, so in general, we can only have a so here we need to assume C2 cofinite. See, now we assume that the modules are C2 cofinite. If the modules are C2 cofinite, only finite dimensional a finite dimensional subspace cannot be written in this form, right? Only finite dimensional, and these finite dimensional must be weight must be less than some number, because if you have elements for arbitrary weights, arbitrary higher weights, then you see you certainly will have infinite dimensional subspace. Because you only have finite dimensional space, these elements must have weight to be less than some number. So basically is that we say that if for every element whose weight is larger than some number, it can always be written as a linear combination of elements of this form, V2, V minus 2 applied to W1. And then you see that you can reduce the pseudo Q trace to the pseudo Q trace of weight for elements of weight less than the elements we start with. So if you continue this process, eventually you reduce only to those series, the pseudo traces obtained from elements in modules of weight less than some particular number. Okay, and then see for these modules we consider the subspace of weight less than certain number finite dimensional. Okay, and therefore we will actually obtain a finite dimensional vector space, and so now we actually need to look at the coefficients. These coefficients are either these Eisenstein series or the derivative of Weierstrass P function. So basically, we actually using the Eisenstein series and a Weierstrass P function, we actually generate a ring, and for this ring, using this ring, using these finitely many Q traces, we actually generate a finitely generated module. Okay, so we see that all these pseudo Q traces, they form a finitely generated module over the ring of Eisenstein series and Weierstrass P functions and their derivatives. Okay, so using this formula, we obtain this conclusion. Okay, now so this is very nice because now we obtain only finitely many such Q trace. We need to prove a convergence because all the other pseudo Q traces can be written as a linear combination of these. And then for these finitely many, if we want to prove their convergence, we still need to derive differential equation. So in the case of product intertwining operator, we actually use the derivative with respect to these z's. Okay, these z derivative with respect to z corresponding to L minus 1 applied to the elements. Here certainly you can also take a derivative with respect to like z1, z2. So indeed.
Sorry, can I just ask a question?
Yes, sure.
So it's about the importance of it, the Weierstrass P function appearing here. So is the idea that to prove this formula, you can write the difference of the two sides as a combination of traces of triple of terms, two intertwining operators and one vertex operator, and then use sort of circulating trace to move the vertex operator around and get some cancellation using ellipticity. Yeah,
the idea is that you write, you sort of like the here V minus 2. V minus 2 is something like the residue x minus 2 and x. So this is the V minus 2. You put this here, and then see this is something like you have a locally you have a meromorphic function, and then you want to sort of move to the outside. Okay, so here. So here let me just say that there's one really subtle thing is the following. We can abstractly define what is a correlation function on such a torus. You just use the vertex operator combined with the meromorphic function, which is a Weierstrass P function. So you can define abstractly what is a correlation function. Correlation function should be some function, some map from these modules, depend on these points and also Q, and then see the such that when you take some kind of integral like the residue of some rational the meromorphic function, you will actually get it. This must be equal to 0 or something.
Right.
So this abstract definition, it's actually quite easy to define. Okay, so this is something like you can find these things in, say, for example, Drew has a paper he defined so-called the global intertonial operator on the Riemann surface, but actually what he defined is just the correlation function of arbitrary Riemann surface. And also in Benzivi and Franco's book, they also have this kind of definition. The main difficulty with this type of proof is that this type of deriving these does not help, because we start with these are just a formal series. These are not a function. Okay, if you have a function, then it should satisfy this property. These are not functions, these are formal series. So you have to use each individual property of the intertwining operator and the property of trace to actually obtain the same formula as you obtain as you defining these correlation function. So that is the hard part. One actually has to prove this. So the nice thing that when you have this kind of a residue, and then you can use the so-called the Jacobi identity for the intertwining operator. The Jacobi identity for the intertwining operator give you see this kind of a residue will move to here and here, and then the kind of a residue here you can use the Jacobi identity for this Y2 again, and then it will actually act on this W2. Okay, but there's one point you will come to here. How do you deal with this one point? You have to use first of all, you have to commute with this QL0, but that's easy. But then you have to use the property of a trace. Trace is symmetric. So you can move to this point here. And when you do this process, the interesting part is that when you do this, originally the Jacobi identity involved this rational function on a sphere. And when you do these, you will have this infinite sum of this rational function, and this infinite sum turn out to be exactly this Eisenstein series and Weierstrass P function. So the derivation, actually, you have to work with definition of intertwining operator, but the result is indeed agree with just this abstract definition. So that's what's going on.
Okay. I think I understand. All right.
Okay.
Thanks.
So, okay, now this procedure actually reduces the study of these general pseudo trace to study of finitely many of them. Okay, but in the case of product of intertwining operator, we actually take the derivative with these z's, then we obtain differential equation. But here we can certainly also take derivative with z, and we do obtain differential equation. But this differential equation cannot be used to prove this convergence, because this convergence is for this as a Q trace. So we actually have to take a derivative with respect to Q. Okay, so now see, this is not something trivial, because if you take a derivative Q, you will have some L0 inserted here. And what is the L0 acting on this? That's complicated. So this involves another formula. So the other formula is, okay, let me see I probably, so the main thing is that we actually obtain this formula. So probably I will, because I do not have a lot of time, so I will not write down the full formula, but let me just write down something that is this point. We actually can prove that 2 pi I square and then trace phi w of this L0 minus C over 24 y 1 of this U of E 2 pi I Z1 W1 E 2 pi I Z1. Okay, so I think that I will write this part. It's the same, so I would not write this. I would just say this to make this simpler. So the main thing that we can actually prove that this is actually equal to equal to what? Equal to the same kind of a pseudo trace with, okay, certainly we have y1, y2, and a ql0 and so on. So I will not write all of them, but the main thing that you will have some action of something acting on w1. And the things acting on w1 are actually something like like a Virasoro operator, L minus 2, or L0 plus L minus 1Z1, something like this. And the coefficients, there will be some coefficients. Coefficients are also the Weierstrass P function, these are P tilde, okay, these m plus 1, and so on. And also, so there are a number of terms. Also, there are these these things, the Eisenstein series. Okay, so there are a number of terms. It's more complicated than the formula I wrote out. You can actually obtain this kind of formula. Now, the main thing that the nice thing is the following. We actually have this L0 minus C over 24. Where this minus C over 24 coming from? Because here, originally there's the vertex operator. This vertex operator, you also have to put this U of this. This U of this actually produce this. So because of we have this L0 minus C over 24, you actually have to change here to C over 24. But see, this is on both sides, you just multiply. Okay. And then this side become the derivative. It's the derivative like the Q ddq, right? It's become this Q ddq, and then the equal to the right hand side. Okay, so here I just want to mention one subtle thing. One very interesting thing is the following. In the formula I wrote down before, you see that these like the Eisenstein series, which is for K's belong to Z plus. So these are modular form because the K is at least equal to 1. So this is like a G4, G6, and so on. And here it's M is in, let me see, I think, here it must be, okay, I think this should be like M in plus 2 or something. Okay, so the main thing that when M equal to 0, this is the Weierstrass P function, and then its derivative. So these are all the usual the meromorphic function on the modular space of genus 1 surface. But here, okay, the difference here is that in this case, K can be equal to 0. Okay, it is possible K to be equal to K equal to 0. We have G tilde 2, or which is corresponding to G2 tau. G2 tau is not a modular form. And also here, M is allowed to be equal to 0. So in this case, P1. P1 is the Weierstrass zeta function. Okay, so you see, in the beginning, you see that these things are not modular invariant. It's bad. But on the other hand, it's actually good. Why? Because this derivative is also not modular invariant. And actually, you will put this P1 and a G2 to the other side to combine with this derivative. Putting them together, they form differential operator. That differential operator is actually modular invariant. So this is really wonderful because we know the modular transformation of this. We also know the modular transformation of these. And then you can also calculate the modular transformation of this derivative. They actually exactly sort of cancel with each other. They form a modular invariant differential operator in a certain sense. So therefore, okay, now it's very nice. If you move this everything to there, you actually get some differential operator acting on these trace is equal to, the only difference is that here you change the elements W1, W2 to some different things. And then you know that we can further write these as linear combination of these finitely many of them, and then we obtain differential equation. So this is the way to obtain our differential equation. So this is a much more complicated because so first of all, the calculation is complicated. Second is that you have to be very confident to be able to carry out these calculations. Okay, so roughly speaking, now this is the proof. This is the proof of the convergence. Basically, this is both in the case of a rational case and a logarithm case. For the convergence part, they are almost the same. Okay, so after this, the convergence part, what I want to talk about is already finished, but I just want to mention. So after this convergence is approved, because of the differential equation, the coefficients are just these Weierstrass P function and these modular form. So the sum of these series actually can be analytically extended to the region. Like in this case, we have Z1, Z2, and Q. So to the whole region of Z1, Z2, ZQ, except at this singularity point, like a Z1 minus Z2 equal to like the m plus n tau. For these points, they are actually the singular point. So here tau, here Q is equal to e to pi I tau, right? So because the reason why these are singular points is mainly because our Weierstrass P function actually has this singular point. Okay. Now after this is established, then we can try to prove the modular invariance. So in the case of rational case, I proved the modular invariance. Okay, so means that under the modular transform, the space of these traces are actually the same. Okay. Then see in the logarithm case. Okay, in the logarithm case means that the module does not have to be completely reducible, but but we still have C2 cofinates, and together with one condition that the vertex operator must have only positive weight states and so on. Under this condition, see Francisco already proved this convergence. Okay, but there's the other step that to prove this modular invariance. So this modular invariance, I think I will actually finish very soon. So it's the main thing that originally one important ingredient missing is some kind of more general type of associative algebra. So I actually for the last 2 years I developed the whole theory of associative algebra, and then applied to the intertwined operator, applied to these pseudo traces, everything works out. So I'm still writing the paper to actually finishing the paper on the modular invariance. So at least for the logarithm C2 logarithm case, soon so we will have the proof of the modular invariance also. Okay, so its time is up, so I have to finish here. So the next time I will discuss first of all briefly the convergence associated to the arbitrary local coordinate sewing, and the convergence related to the conformal anomaly, that's the central charge, and also briefly discuss the results of Gui on high genus convergence, and then I want to present these conjectures and the problems on orbifold conformal field theory, on convergence, and also for the cohomology theory of vertex operator algebra. Okay, I finish here.
Okay, let's thank the speaker. Are there any questions? Comments? Jethro, there are questions?
So, would you be able to comment again on the function, the symmetric function phi, and the definition of the pseudo trace function? So, is it a symmetric function on some fixed algebra, or what? What exactly is?
So the main thing is this: to define the pseudo trace, we have to choose an associative algebra P, which acts on the module commutes with the vertex operator. Okay, so you choose arbitrary such algebra, and you choose a phi. Okay, you choose a phi which is symmetric linear function on this P. So for each P, certainly the P should act on the module projectively. But see, for each such P, each such action, each such symmetric linear function, we have a pseudo trace. Okay, and then you choose different P, different phi. You have different pseudo trace. The modular invariance is that you have to consider these pseudo trace for all phi, all P, and so on. And then you see these form a vector space, and this huge vector space is invented under the action of the modular group.
And it's necessary that the module be projective for this algebra.
Yeah, because otherwise we cannot define. We cannot even define the pseudo trace. You have to choose. You have to choose a projective action.
Yeah. Okay. Thanks.
Okay, so let's thank the speaker again.
Okay, thank you.
And we'll resume in 25 minutes.
Yeah, 3 o'clock. So now there's tea and coffee and cake in the tea room. Thanks again, Yujit.
Okay, thank you.